In this podcast, we're going to talk about heating and cooling curves and what they are, and how to interpret them, and how to draw them, and then how to use them to calculate heat added or released from a system as it changes temperature or changes phase. So this is a heating cooling curve. This one is for cooling. And we know that because the temperature is going down progressively, so it is cooling. And it starts out as a gas, and in this case it starts out as a gas at 130 degrees, and the substance is water. So therefore the boiling point for water is 100, and the melting and freezing point for water is 0. We start out at positive 130, which is the gas phase, and notice that these pictures have nice particle diagrams that show you that the gas particles are far apart and they're moving quickly, bouncing against the walls. And when we remove heat from our gas at 130, it's going to cool down, and it's going to keep cooling down. The slope is going to be negative until it gets to 100 degrees. Because at 100 degrees, it starts to condense, because 100 degrees is the boiling/condensing temperature for water. And as it changes phases, as it condenses, the temperature is constant. So in this section here in stage 2, it's going to be made up of both a gas and a liquid, 2 phases, because it's phase changing. Notice that the liquid is the particles are close together, but they're moving and they're not lined up. They're all disorganized, but touching each other. And we have a liquid in combination with a gas. So during phase 1, the gas is cooling, and then during phase 2, we've got gas converting to a liquid, which is condensation. And during the phase change, the temperature is constant, and this is really important. You can either be changing temperature or changing phase. You cannot do both at the same time. Okay, the next section. So at this point, on the left of the phase change, everything's a gas. And then as we get to the end of phase 2, at this point, everything is now a liquid. So now that everything's a liquid, it can then continue cooling down. The temperature can change. So in stage 3, it is a pure liquid. The liquid is cooling, so the temperature is going down, and it's going to go down from 100, where it starts cooling, and it's going to keep cooling and keep cooling and keep cooling until it gets to the melting point, melting/freezing point, which is 0 degrees. So notice the particle diagram. It's a liquid, the entire phase. And again, we draw a liquid. The particles are touching each other, but they are not lined up together. So at the end of stage 3, everything is down at 0, and it's going to start to freeze. And because, again, it's a phase change, the temperature is going to remain constant. So as it freezes, it starts out as a pure liquid. During phase 4, it is liquid and solid together. And then as it gets to the end here, everything is going to be a solid. So again, we see 2 phases in the phase diagram. We've the liquid, which is the big sloppy, particles touching but not lining up. And then we see this piece in the middle, where the particles are rigid and all lined up and hold their own shape, and that would be the solid. So in this phase 4, it's going from a liquid to a solid. Both phases are present during the phase change. We call it freezing. And again, because we are phase changing, the temperature has to remain constant during the phase change. So here we are at the end of phase 4. Now everything's a solid, and then the temperature can keep going down, and that's what happens in stage 5. So the solid is cooling. It can go down, forever, as long as we can get it. In this case, it's going from 0 down to -40, minus 40 degrees Celsius. So that is a cooling curve. And at the bottom of this page, you guys are going to draw a heating curve for ice. So again, for water, it's going to have melting point at 0, boiling point at 100, like normal water, and start at -30, and then heat it up until it gets to 160 degrees Celsius. Label all the phases and all the temperatures. You don't have to draw particle diagrams, but you could if you wanted to, but it's hard to fit it all in. But definitely label all the phases, label all the temperatures, and label all the phase changes. So you can shut off your video and then try it yourself and then turn it back on and check and see how you did. So we're going to label the temperature along the on this axis, and this is the progress of adding the heat. So in the first stage, start out at -30, so it's going to start out down here. It's going to be a solid, and it's going to warm up, and it's going to keep warming up until it gets to 0, which is the melting point of water. And then the next stage is melting, and during the phase change, the temperature is constant. So that is the melting. It starts out as a solid, and it's going to end up as a liquid. Once it has all melted, then the temperature can keep increasing, and it's going to go from 0 all the way up to 100, which is the boiling point for water. And during this stage, it's going to be a liquid the entire time. Once it gets up to 100, we are at the boiling point, and then it can vaporize or boil. Same thing. Phase change, temperature is constant, vaporizes. And then once everything has vaporized, then the temperature can continue to increase, and in this case it's going to go up to 160. So we don't usually worry about the scale so much of the temperature. Just label all the important temperatures that we care about. You don't have to label every 10 degrees or something like that. And because we're not calculating the slope or anything, we don't worry too much about the scale. You just want to spread things out so that you have a lot of room to draw your curve, and make sure that you show either temperature is changing, temperature is increasing in this case, or we're in a phase change, and during a phase change the temperature is constant. To label all the phases that are present during each stage, solid is warming up, phase change, melting goes from solid to liquid, so both phases are present. Then the liquid is going to warm up to the boiling point, and then again during the phase change it's going to be a liquid and a gas present, and then the gas can warm up to 160. So now that we know how to draw diagrams, the reason why we draw each stage separately is that each stage requires its own separate calculation. If we have the temperature changing, we are going to use the Q for the temperature change, where phase is constant, and that equation is Q, which is heat, is mass times heat capacity times delta T, which is the change in temperature. And the reason why we have to do all the Q's separate, we cannot combine them all into one big calculation, is that for each phase we're going to have a different C. The heat capacity actually changes if we're talking about a solid or a liquid or a gas. The water heat capacities are given here, so that because we're going to use these fairly often. Heat capacity for ice is 2.05, liquid is 4.18, and the gas is 2.08. You don't have to memorize these, they're always going to be given, but just keep in mind that you want to make sure that you know what phase you're in so that you have the right C. So to do some examples of calculating Q, where temperature is changing, example 1, is calculate the heat required, so we're going to be adding heat to warm up 12.5 grams of ice from -15 up to 0, which is the melting point. So we're not going to be melting, we're just going to be changing the temperature of the solid ice, and the mass is 12.5. So because it is ice, the C that we're going to use is 2.05, so be really careful to grab the right one. So Q, which is heat, is going to be the mass, which is 12.5, times the heat capacity of ice, and then the change in temperature is 15 degrees Celsius or Kelvin. They are both the same if we're talking about change in temperature. And because I want my units to match, I'm going to use Kelvin here so that I can see that Kelvin, degrees Kelvin are going to cancel. And I'm left with heat, and we are going to calculate heat in joules. Keep in mind that you could also calculate heat in calories. And to do that, you would need heat capacity that was listed for calories. Okay, next example. How much heat is released? Releasing means the heat's going to go down. Heat's going to be removed, which means the temperature is going to go down. When 275 grams of boiling water, so water at its boiling point, which means it's at 100 degrees, is cooled to body temperature, which is 32. So this would be an example of if you got splashed with boiling water. That water would hit your skin, and all that heat would have to go somewhere. And in that case, it would go into your skin, which is why it would burn you, and that would be dangerous. So how do we calculate this? We're talking about liquid water. So the C for liquid water is 4.18. The change in temperature is the difference between 100 and 32, and that is 68. We are going to use the absolute value here and not worry about the sign changes. We're just going to calculate the quantity of heat, which is for 68 degrees Kelvin. So Q is going to be mass, 275, times C, 4.18, times 68, which is the change in temperature, 78,166 joules. Joules are really tiny, so the numbers can get really, really big for joules. So to avoid such large numbers, we often take joules and then divide them by 1,000 to convert to kilojoules, and that's going to be 78.2. 3 sig figs for kilojoules. If it doesn't specify, you can report your answer to in either joules or kilojoules. Okay, so the other Q equation that we are going to use is the Q that we could use for phase changes. So the temperature is not changing, but the phases are. And that equation is Q equals mass times delta H. There's two different delta H's, and you have to use the right one for the right phase change. If we're talking about condensing or vaporizing, we're going to use the delta H of vaporization, or delta H of vape. If we're talking about freezing or melting, we use the delta H of fusion. So make sure that you know what phase change and that you use the right one. So in this example, calculate the heat released. So it's going to be released by the system when 42.4 grams of water is frozen. So it's going to undergo phase change from liquid to solid, which is freezing, into ice at 0. So Q equals M mass times delta H, and because we're talking about freezing, it's going to be delta H of fusion, 42.4 grams times 333 joules per gram, and that is 14,199 joules, or 141 kilojoules. And again, conversion to kilojoules can be useful when the numbers get really, really big. Okay, the last one, calculate Q to evaporate 72.5 grams of water to steam at its boiling point. Because it says evaporation or vaporize or boiling, we are going to use the delta H of vaporization. Q equals M delta H. Mass is 72.5. Notice that the delta H of vaporization is huge, 2,257 joules per gram. So that makes the answer 1.64 times 10 to the 5 joules, or 164 kilojoules. The reason why it takes so much energy to vaporize water, remember that water has hydrogen bonding, so it sticks to itself really, really well, and you have to break all those hydrogen bonds to get it to vaporize, and that's why it takes so much energy here. So now we're going to put them together. So if we have ice, 65 grams of ice at minus 20, and then we're going to heat it to a gas at 155. So now we have to go through all of those stages. So we can't go directly from an ice to a gas. We have to increase the temperature and change the phases. So the first thing that you want to do is write a phase diagram. And what I've done here is do the phase diagram in stages, the heating diagram, and then calculate Q as we go. So the first stage is ice at minus 20, and it will warm up to 0. So it's going to be a solid as it's warming. So the Q equation is going to be mc delta T. C is going to be ice, and then we calculate the joules for that process. The next stage is melting. So once the ice has warmed up to 0 in stage 1, now it can melt. And that's going to be stage 2, which I've labeled 2. And that is Q equals mass times delta H of fusion. Because we're talking about melting, we're going to use delta H of fusion, which is 65 times delta H of fusion, 21,645 joules. Just calculate all the joules individually, and then when we're done, add them all together. So continuing, now the liquid can warm up from 0 to 100, and that's going to be mc delta T, because we're in a temperature change. Calculate that. The next stage, now that everything is warmed up to 100, it can vaporize in stage 4, and that's going to be mass times delta H of vaporization, which is 65 times 2,257, which is a huge amount of energy. This is usually the big one. Vaporizing takes the most energy. And now that it's a gas, the gas can warm up, in this case to 155. So it's going to be mc delta T. Remember that C, heat capacity, has to be for the gas here because it's in the gas phase. And then once we're done, take all the Q's individually and we're going to add them together. So the total amount of heat is all the individual heats for each stage added up. Plug them all into your calculator. I do not round until I'm totally finished. In this case, I rounded to 3 sig figs. And so it's 2.06 times 10 to the 5th joules, or 206 kilojoules. So these can be quite a bit of work. Give yourself a lot of room, more room than I did here. And they're a bit tedious, and you want to keep track of all your units. And definitely the heating or cooling curves make it make the calculations make much more sense. Okay, next example. Now we're going to release heat. 275 grams of steam at 100 is cooled to a liquid at body temperature, which is 32. So we have steam at 100. We cannot cool steam at 100 because to cool, it has to be a liquid. So the first stage is going to be condensation. So you've got steam at 100. It has to condense to a liquid. That's going to be Q1. Because it's a phase change, it's going to be delta H. And calculate that in joules. And now that it's a liquid at 100, then it can cool down. In this case, it's cooling to 32. Liquid cooling, Q2, and that's going to be MC delta T, change in temperature. And then for the total, again, we're going to add these two Q's up together, Q1 and 2, and that gets us 6.99 times 10 to the 5th joules, or 699 kilojoules. Note, in an earlier example we had boiling water, and now we have steam. And the amount of heat released from steam is huge, and that's why steams can cause such horrible burns, much worse than boiling water, even at the same temperature, because all that heat from the steam has to go somewhere, and that's very dangerous. Okay, so on the next on the next page, there's two examples. What you want to do for these is turn off your video and try them yourself. Definitely draw a heating or cooling curve first to figure out what the Q's are. All the data is going to be given. Keep in mind that you could be given data that you don't end up needing, so be really careful. Note that the C's are different for the liquid or gas. And these are both not water, so they have strange numbers, different melting points, different boiling points than we're used to seeing for water. The first one is for methane, fuel, and then the second one is for ethanol. So stop your video and then try the math and then turn it back on and check your work. Okay, so there are 4 different stages. It's going to melt, and then the liquid's going to warm up, and then vaporize, and then the gas is going to warm up. Be really careful with your temperatures. These are negative temperatures, which can be a little bit tricky. Just label the temperatures that we care about. Don't worry about the entire scale. It's going to give us 4 sections, 4 different Q's, calculate them separately, and then add them together to get 90.5 kilojoules, or 9.05 times 10 to the 4th joules. Okay, for the next one, it's going to be ethanol. Again, the data is given. Draw a heating cooling curve before you start, and turn off your video, and then turn it back on to check your work. So this problem, it starts at a gas at 300, cools down until it gets to the boiling point, where it condenses into a liquid, and that's Q2. Then the liquid can cool down, in this case, to 25. It doesn't get all the way to the freezing point. We're not even given the freezing point, and it goes down to 25 degrees. So it has 3 stages, so 3 Q's. Calculate them separately, and then add them together to get 1.46 times 10 to the 5 joules, or 146 kilojoules.